Okay, so it's 2:02 right now. Let's get started. We have 70 attendees. Looks like this is a very popular talk. So hello everyone, welcome to ASIC seminar series. This is John, the seminar coordinator. I will be moderating this seminar with our communication specialist, Cassie. Cassie is our communication manager, and she will be moderating the seminar with me, and she will take care of the Q&A sessions afterwards. Just so you know that, after the presentation, we'll have the Q&A, and we encourage you to bring up any questions you may have. And you can unmute yourself and ask a verbal question. Or if you don't have a mic, you can chat out your questions and we'll read them out. Our Associate Director, Ralph Ferrero, also joined us and he will be introducing the speaker. What else? I think, I'm going to turn this, give the ball to Ralph. And Ralph, please go ahead.
Yeah, thanks, John, and welcome, Lucas. So we have Dr. Lucas Harris from NOAA's Geophysical Fluid Dynamics Lab in Princeton, New Jersey, where he serves as the Deputy Division Leader of the Weather and Climate Dynamics Division. He's going to tell us about his work and also about the FV3 activities. And let's see, he's got his PhD, University of Washington in Applied Mathematics, and he recently won a Atmospheric Science Ascent Award from the AGU this past December. So we'll hand it off to Lucas. Look forward to the talk.
Well, thank you, Ralph. Thank you for setting it up. One minor correction, my PhD is actually in atmospheric sciences. I have a master's degree in applied mathematics.
Ah, okay. All right, I misread that. Thanks for correcting that.
Okay. So can everybody see my slides full screen?
Yes, that looks great.
Okay, fantastic. Thank you so much. Thank you for giving me this opportunity to speak today, and thanks to John and Cassie for setting up this opportunity for me. I also want to thank my partners, both in GFDL and in the broader community at a number of different places, and my project co-leads here in the FV3 team, Linjiang Zhou and Jianhui Chen. So traditional global models have been used for many years for large-scale prediction. And here's an example from our 13-kilometer SHiELD model that we run in real time on our real-time website. You can also go down to regional scales and start to simulate explicit thunderstorms and other convective scale features and other intense features as well, traditionally done with the regional model. But then you have the question about if you want to go from the larger scales down to the smaller scales and then back up again, the feedback of smaller scales to the large scale, how can you do that? And traditional GCMs, traditional regional models really can't do that. But you can do these things with global nested models and global storm resolving models, which will be the main theme of my talk today. So to introduce the NOAA Research Global-Nest Initiative, this is a multi-center initiative funded within NOAA Research to develop storm-scale holistic seamless digital twins of the Earth system for prediction, projection, and understanding of extreme weather events, and to create actionable information at all time scales. And that's basically the buzzword for compliant way of saying that we're developing new classes of numerical models. Both our global nested models that you can use for medium range and S2S prediction, as well as for global storm resolving models that are run at kilometer scales, able to simulate explicit convection worldwide, as well as other efforts such as developing hectometer or sub-kilometer scale multi-nested process models. And we have the NOAA Research, the Global Nest Initiative website here. You can see more information about that there, or read our technical report as well. The Global Nest Initiative is founded on a couple of key technologies that I'll come back to. I'll introduce a few of them here. FV3 Dynamical Core, the SHiELD weather to subseasonal model, the FMS framework, and something I'll discuss a little bit later is PACE, which is a new rewrite of all these technologies in Python for performance portability. And I'll discuss that a little bit later. So we do all of our work around the FV3 Dynamical Core, this GFDL finite volume cube sphere dynamical core. This is a dynamical core that's used in a wide variety of atmosphere models around the world, especially global models in NOAA and NASA. I know our fantastic partners at NASA Goddard and at the Environmental Modeling Center develop global models around this, as well as us here at GFDL and elsewhere. FV3 is a fluid solver or engine, kind of more generic ways of saying the dynamical core, which has a number of different powerful features, accurate numerics, advanced thermodynamics. It's very computationally efficient, very flexible solver and interface capable of implementation in a lot of models with a lot of advanced grid capabilities. And this gives you a lot of advantages for developing, especially increasingly high resolution models, timely forecasts, accelerate your development, run your model faster, you can debug and rerun it faster, go to increasingly high resolution, and you can apply it to a lot of different applications that have been done across all the different users of this. Here's two examples. This is atmospheric composition forecasting in NASA GEOS, which is actually the first FV3-based system, going way back to the FV era back in the late 90s, as well as in our GFDL SPEAR coupled climate model, in which you can do time slice integrations, or you can do seasonal to decadal prediction as well. As I mentioned, the worldwide community here using a number of different centers, and also our continued open development through the FV3 community GitHub, a hub for all of the different development that goes on with this dynamical core and inclusion into other models. And I like to summarize this and our other different collaborations by a quote by Morris Bender, the longtime lead of the GFDL hurricane model operational for many years, that a key element that makes collaboration successful is having individuals who enjoy working together and are able to do so. And I think that's the fundamental idea of community. And I think it's one of the things that have made our own FV3 community, as well as other communities that it collaborates with, that it federates with, very successful. One of the advantages of the FV3 is that its numerics are very physically realizable. And that it has a very high numerical accuracy as well. And this is reflected easily through the kinetic energy spectrum of FV3-based numerical models. So again, FV3 is only a dynamical core. It takes a whole holistically developed model to give you good results. This is something that you can attribute usually to the dynamics itself, modulo some up and down changes due to the physics. And you can see this clearly that one of the big advantages of FV3 is that it produces a lot of these physical changes that allow you to capture that minus 5/3 mesoscale spectrum that you can see right along here, this right here. And that's something that's captured very well in the FV3-based operational GFS in gold here, as well as our own SHiELD model that we run here at GFDL. There's a slightly different diffusion characteristics in the two, but they both get a 4 delta X cutoff and this minus 5/3 spectrum. And that wasn't true in the legacy spectral GFS, the 13 kilometer here in the blue, or even the higher resolution European center model, which doesn't have much of a mesoscale spectrum. And this really shows you some of the immediate power of what a dynamical core like FV3 can provide for you. FV3, as I mentioned, has been implemented in a lot of different models. It's been implemented in the GFS since 2019. It's in the operational HAFS, the hurricane model, as well as our own experimental models, SHiELD, T-SHiELD, and so on that we develop here at GFDL. And one of the biggest advances in what's gone on since the implementation of FV3 and a lot of other community changes is that the GFS in particular has substantially caught up to the European center in terms of Atlantic tropical cyclone track forecasting. The gap has been substantively closed. You actually get a little bit better even with the 13-kilometer SHiELD. And this past year, actually, again, the GFS at 120 hours was able to beat the European center in terms of Atlantic track forecasting. Furthermore, the operational HAFS, another FV3-based model for moving nested grid, and our experimental T-SHiELD with one big static nest, both have good intensity and good track skill. In particular, T-SHiELD also matched the European center again this year. And now, all these great results, I do want to provide the big caveat. Two things I want to mention. One is that this is a long period of samples. This is a 5-year sample for both pre and after, so that we can eliminate the effects of interannual variability. Some years models can do better than others. And this shows pretty consistently that, yeah, the United States has been able to catch up with the European center. The other thing I want to mention is that it's not just dynamics. We just didn't plop FV3 into this and made everything better. You cannot do that. Models are not plug and play. You need to develop the model together as a whole: dynamics, data assimilation, physics, infrastructure, and all sorts of other things. That effort altogether is what makes these models successful. It's not just you just shove in a new dynamical core and it makes things great. So this is truly a massive team effort that we're watching here. Going farther, we want to go down even farther down the spectrum, and here's some examples using the simplified form of FV3 Dynamical Core with some physics, basically usually a simple microphysics. Here's a paper we published on tornado-like vortices in a super stretched global idealized FV3. This stretches down to about 1 kilometer or 2 kilometers or 500 meters, depending on your choice. And it shows these excellent structures that are dynamically very similar tornadoes, even if the scale is a little bit too large, because you can't represent a 500 meter wide tornado vortex in a 1 kilometer grid spacing model. But this does show the great power of FV3 to simulate these rotational modes that govern a lot of the extreme weather. And you can go beyond that. You can use our doubly periodic domain to set up a radiative convective equilibrium or large eddy simulations. And this is a very powerful foundation for process models in which you can take a look at convection when it's truly resolved down to 250 meter resolution and see what characteristics you get from that. So some exciting things you can do all within the same framework. I do want to briefly mention FMS. I mean, I could give a whole hour's presentation on FV3, FMS, SHiELD, and PACE. I don't have that much time, unfortunately, but I would want to mention the power of the FMS framework. And that framework allows us excellent scaling out to hundreds of thousands of MPI ranks or out to millions of threads if you have a system big enough. This was first demonstrated 10 years ago with the older HiRAM model on Argonne's Blue Gene Q, then the largest system in the world. That you can scale linearly, a 3.5 kilometer model, close to linearly, out to 85 days per day with over a million threads. And then in more recent systems, we've been able to scale out on our new relatively new C5 system here at GFDL, a 3.25 kilometer solo core, just dynamics. And it scales again close to linearly out to 230,000 cores, which gives us 197 days per day or 7.3 minutes per day. And this is following the philosophy of FV3's creator, S.J. Lin, that a good model must be a fast model. And you can have a fast model that maybe isn't great, but to be able to make it good, it's got to be fast so you can actually get that turnaround. You can fix things faster in that case. So now I want to mention our SHiELD model. SHiELD stands for System for High Resolution Prediction on Earth to Local Domains. This is a seamlessly unified model with the GFDL Seamless Modeling Suite of climate and coupled models, as well as with the Unified Forecast System. It's non-hydrostatic FV3 coupled to a modified form of the GFS physics, including the GFDL microphysics, which you keep updating. The whole idea is that there's one system, one code, one executable, one workflow, one physics, and one basically essentially one unified system that allows us to do a lot of different things with just this one code base. You can see a number of different applications here. One of the real things is that it allows us to demonstrate new capabilities and applications using the FV3 Dynamical Core and our physics development. And the thing I really emphasize is that improvements in one of these systems that we do usually yearly, we roll out a new version every year or so of at least one of these configurations, helps to improve all the other configurations too. They all build upon one another. This is what I call holistic seamless. You holistically develop a whole modeling system where everything depends on one another, but can help improve one another. And we do this for real-time forecasts that are submitted to intercomparisons like Diamond and Dimosic, test beds like the Hazardous Weather Test Bed and HREX. And I kind of like to summarize all this as this quote from a blogger, John Gruber, that making a little bit of improvement every year gets eventually to big improvements added up over a couple of years, like the effect of compound interest in a bank. It all adds up. So you can see more information here at the SHiELD website if you would like. Our newest version is the 6.5 kilometer SHiELD, which is our flagship global model. This is the foundation for all the global nest applications we're going to show you. This builds upon our success with the 13 kilometer SHiELD, which is in the previous results. This runs 4x daily, starting December of last year, 10-day global predictions of extreme events worldwide. This is the first Global-Nest Initiative deliverable. And we both sustain our good global large-scale skill, but also get improved representation of extreme weather events. Tropical cyclones is a big one. This is a global model that is getting tropical cyclone intensity skill. We can represent mesoscale convective systems, local circulations, heavy precipitation, like these improved results for CONUS precipitation skill you see here. This is published in an article by Linjiang Zhou that came out late last year in James. Here's some eye candy to really show you the difference between 13 kilometers and 6.5 kilometers for events all around the world, from things like a coastal convection here in the United States. You can see the effects of a marine stratocumulus. You can see finer scale features quite a bit at the 6.5 kilometer resolution there on the right-hand side of both of these two panels. You see improved representation of baroclinic cyclones, as well as free tropical convection over the Amazon. And these are produced again in real time 4x daily. So you can see the newest forecasts at this website, shield.gfdl.noaa.gov. Another thing that we did is this collaboration with the European Center, and they let it lead a project called DIMOSIC, different models, same initial conditions. And this is an international intercomparison of global prediction models, all initialized from the same initial conditions, in this case, the European Center's excellent analyses, which are admittedly the best in the world. And the European Center, it's their native analysis. So when they run their model called the IFS, they actually get pretty good results for various top-line measures and tropical cyclone forecasts. The thing that we did find is that SHiELD also performed very well with these European Center initial conditions. This is run over a period from like 2018 to 2019. We were able to represent this tropical convection quite well in this case with relatively low errors compared to many of the other models, as well as a very good tropical cyclone skill on par with, again, the European Center. And this is, I should point out, back in a time before we had the excellent GFS initial conditions that were getting us much better tropical cyclone skill in the recent 5 years. The big thing, one of the big reasons for that is that not only do you have a very solid model, but also very careful implementation of those initial conditions in FV3 and in SHiELD. Again, this is the idea that models are not just plug and play. You can't just shove a better analysis in a model and get a better result. There's a new phase of DIMOSIC coming up that is currently being planned. We're really excited about that. I know that EMC also plans to participate. We're hoping that they can play too. I know they've got a lot of other responsibilities too. So thank you, everybody. Okay, so that's the foundation. Now we want to move on to global nest applications. And what do we mean by global nesting? So FV3 supports a couple of different variable resolution global modeling techniques. The first one that I'll talk about is what is our two-way nesting. We have a global domain and a regional higher resolution domain that fits within those, and the two domains exchange information in a two-way sense. And this allows that both the global scales to be represented consistently, as well as capturing the higher resolutions, in this case, 3-kilometer storm scales. That allows the two scales to feed back into one another and get best consistent representation done efficiently enough that we can run these in real time. Nesting is quite a flexible thing. You can choose your time steps in physics and other choices for each nest individually. You can even put in multiple nests. You can do telescopic nests as well. So you can zoom down to increasingly high resolution. Here's an example we call teleshield, where we zoom down 1.4 kilometers over the Northeast corridor here in the United States, over Taiwan. Also, another example of nesting is the moving nested grid in the excellent HAFS model developed by our partners at EMC and AOML. They've been working on the moving nested grid, as well as moving nested grid in the global domain, an experimental feature, which can follow a tropical cyclone and just give you the resolution where you need it. So check out this article by Bill Ramstrom. It's really, really, really good. Bill Ramstrom's our partner at AOML. Another alternative approach to higher resolution is what's called grid stretching, in which you take the cube of the FV3's cube global grid, and you turn it into a truncated pyramid, the top of which is your high resolution area, your zoomed in area. And this is a somewhat less complicated than running a global nested grid, because you have one topologically identical domain to your original cube sphere. It makes the post-processing and running and setup a lot easier. This has been used a lot for especially chemistry applications. You can see an example in what's called AM5VR by my GFDL colleague Mei Yun Lin. You zoom in over the United States, you get much better air quality predictions over California. It's also used heavily by our partners at NASA in GEOS, and in the community by the GEOS Chem model as well. Here's an example by Liam Bindle at Washington University in St. Louis, of California air quality. So this is all stuff that's immediately available for any FV3-based model in the UFS, in NASA GEOS. It can be used in CESM. Everything is already used and can easily create new nested and stretched grids with standard pre-processing tools, either the free NC tools, UFS tools, or a SHiELD in a box container that includes the pre-processing built into it. So this is a powerful capability that basically comes for free with any FV3-based model. And I really encourage people to check it out, because there's a lot of cool stuff you can do with this. The specific global nest applications, here's something we're working on. Here's our SHiELD model, or contiguous United States nest, 3 kilometers over the US. And this is something that we've gone back to after a few years of working on full speed on some other applications. And we're improving the representation of explicit convective storms for relatively short range prediction, but also medium range forecasting. Here's an example of some of our latest results. This is a plot that was provided by Kai Cheng from the latest version of the model, and that the plot itself was made by Bill Putman and NASA Goddard. So thank you, Bill. They can make some really great stuff there at NASA. They're really good at that. Here's an example of a SHiELD forecast from this past January, 2 months ago. I know it seems like forever ago at this point, but you can see some interesting capabilities in SHiELD compared to the operational HER. And you can see that in particular that the squall line follows very closely where it is in the observations. And also we are able to pick up some qualitative features of the stratiform cumulus shield as well as some of the finer scale features, perhaps a bit more disorganized than in the HER. We're still working on this. We have some really nice improvements that are coming down the pike here soon. We also look at other extreme events. Convective scale is not just for severe weather. There's a lot of other stuff you can do with that. One thing I've been excited about lately is snowstorm prediction. And here's results from a couple of seasons in SHiELD, which can represent the mesoscale circulations around mountains fairly well. We find that we can represent the circulations around Lake Michigan, the Great Lakes in general, as well as in the high mountains in New England very well. The validation does depend a bit on your data set. We found that stage 4 has a bit of a low bias compared to the snow analysis when we apply our snow case criteria to it. But on the whole, we're able to capture these events quite well. The other thing you take a look at is severe downslope winds. Here's an example from the LA fires of a couple of months ago, again, about 2 months ago. And you can see that with our 3-kilometer model, we can capture some of the extreme winds downslope that were fueling these rather awful fires in the Los Angeles area and the surroundings. We're able to capture the extreme winds, not just at short time ranges, but also at 4 days out. Something that beyond operational convective scale models, but also that we're able to capture these winds, and the 13-kilometer models, like a 13-kilometer SHiELD or the GFS, isn't able to capture more. We can capture up to 103 mile per hour winds beyond hurricane force coming off of the mountains, these El Diablo winds. So now we shift to TShield. This is our North Atlantic nested grid model here. Tropical cyclones are a natural for the global nest strategy, simply because tropical cyclones very strongly interact in 2 ways with their environment. In fact, tropical cyclones to some extent influence their own environment, the amount of dry air that they pump out of their tops. It's important to get the interaction between the large scale and the small scale right. We find that TShiELD maintains both excellent track skill and good tropical cyclone intensity. And we're making some good progress on structure prediction as well. I mentioned earlier that both the GFS and TShiELD in 2024 were able to beat the European Center at 120 hours, which is a really cool result that, again, shows the great power of the community. And it gets good intensity skill as well. There's been progress on structure prediction. We're working on things like a precipitation prediction, wind fields, and other factors as well. Now, one of the most interesting things we can do with our large static nest is we can start to think about how is free convection, convective scale motions, affecting the larger scales, the synoptic scale steering flow in this case. And we can found that in this study here by our colleague Kun Gao, that when he changed some of the numerics that changed the qualities of the explicit free convection over the Atlantic, that fed back onto the subtropical high. And that had an impact on steering flow to the point where if you changed too much about how much convection there was, that changed the steering flow and that degraded your track forecasts. So there's this interesting tie between getting those little small scale structures right, but also getting right how those small scale convective structures moisten and heat the largest scale atmosphere that then gives you impacts for your tropical cyclone prediction. And this has implications for longer range prediction using these kilometer scale models that are coming online that I really don't see a whole lot of people really thinking about. And that's something that I think is going to be really important when we start talking about large global nested prediction or global storm resolving prediction on longer scale time features. The only other people, I know that the European Center actually has had some struggle. They run their 1.5 kilometer model with explicit convection, and they do find a degradation in their large scale skill. It's not just you increase the resolution, you necessarily get everything better. Another application using nesting is the Madden-Julian oscillation. This is suggested to me by Tim Palmer. He suggested if I want an improved S2S forecasting over the United States, try improving simulation of the MJO over the maritime continent. Now, you can get a good MJO in relatively low resolution models, like our SPEAR model, for instance, our coupled climate model. The big key is that you need to have a good convection scheme, and you need to have a good representation of the ocean, either a dynamic ocean or a slab ocean like we use in SHiELD, or a mixed layer ocean. But we do find that going to higher resolution does give you better forecasts. So when you go from 100 to 50 to 25 kilometers, you get steadily better MJOs. So what we did is we have this collaboration with AOML. What we did is we ran simulations where we took a 16-kilometer global grid, and we put a 4-kilometer nest over the maritime continent. And we did 40 days forecasts. And this is fairly efficient. We can run a 40-day forecast in 8 hours with 4,000 Gaia cores. This is a somewhat older version in this case. We found that the regular resolution, the 13-kilometer, got a fairly good MJO, got good useful skill out to 28 days. But we found that putting that 4-kilometer nest got us astounding prediction of out to 39 days of useful predictability for these MJOs. These are strong MJOs during the Dynamo event in 2012, 2013. AOML's postdoc, Brianna Zavadoff, wrote an excellent paper on this. We found that the big thing is that having enhanced resolution over the maritime continent improved the precipitation and diurnal cycle, which is what powers the MJO. And that even gets off onto the nested grid, off of the nested grid. So we're going beyond this and taking a closer look at how that feeds into forecasting elsewhere. But this is, I think, is a really awesome result. We can do global nested forecasting of explicit convection of severe weather outbreaks as well. Here are some subseasonal severe storm forecasts we did with a slightly lower version of SHiELD, 5-kilometer nest and a 16-kilometer model. We could explicitly predict severe thunderstorm events, and we do these 30-day forecasts. Again, this is a fairly efficient model. It runs in a couple hours with 2,112 cores. We did 11 30-day forecasts for a 5-year period, and we looked at updraft helicity versus storm reports. And we actually found some promising skill, especially in the northern United States, where severe weather is less common during these times of year. It's not like every week you get a severe weather event in the southern plains. So it's a little bit more predictable in the northern tier of the United States. So we have our excellent colleagues at the National Severe Storms Laboratory. They are working at taking a closer look at these forecasts to be able to look at what's the extended range prediction of explicit weather events out to 2 and 3 weeks, as well as AOML is taking a look at atmospheric river prediction in this model as well. Now I want to move on to our global storm resolving model called SHiELD, the experimental system for high resolution prediction on Earth to local domains. So this is a global storm resolving model, a kilometer scale model. It's the latest in a 15-year series of FV3 based global storm resolving models at NASA and at GFDL. SHiELD has a grid spacing of 3.25 kilometers, explicit deep convection. There's no parameterization of this. It's actually quite efficient. It's more efficient than any other non-hydrostatic GSRM. We are getting 33 minutes per day, or about, let's see here, that's about more than 20 days per day with 27,000 cores on Gaia C6. This allows us to do unprecedented years-long simulations of perturbed climate integrations that we've done some interesting stuff with. This is leveraging both the accuracy as well. You can see the excellent mesoscale spectrum and perfect 4 delta X cutoff in this global SHiELD model. We're able to do like long climate integrations and take a look what their results are. These have also been posted to NOAA's open data dissemination platform in the cloud. I like this quote from Suki Minabe, our longtime climate modeler and Nobel laureate, that if you keep increasing the model resolution but don't make the model more complicated, I think you'll have a great time. And I think we're having a great time with this relatively simple model, but that it can do all the things we need a comprehensive model to do. Brief shout out, we just learned today that the Princeton Global Storm Resolving Hackathon is going to be a go. It's coming this May here in person in Princeton. So we'll be sending out advertisements for that soon. So stay tuned. Here's some eye candy made by a couple of our former colleagues and also Lin Zhangzhou, our lead developer of SHiELD. Fortunately, I don't have a whole lot of time for this, but you can see this is something that you can compare against a satellite image from Himawari. And in particular, you can see tropical cyclones, intense tropical cyclones, as well as a lot of different small-scale convective elements in the cloud systems worldwide. So there's a lot of amazing stuff you could potentially look at in a model like this. Certainly, this is not the only one. I mean, we have the excellent SCREAM model developed by our colleagues at the Department of Energy. That's based on the excellent spectral element dynamical core, a little bit different from what FV3, but also an excellent modeling system. And as well as our partners at NASA Goddard, who also developed these excellent GEOS global storm resolving models. And you can see all of them as part of the Diamond project. What new things can you do with the global storm resolving model? Well, global storm resolving models give you a global view of convection. GCM's traditional global models can't resolve explicit convection. Regional models don't have that feedback to the global scale. GSRMs like SHiELD allow convection to be viewed as a truly global phenomenon. You can do some interesting novel things with this. One is to take a look at rotating convection. Usually in the context of severe weather, we look at that over the United States. But I took a look at rotating convection of relatively low updraft helicity and took a look at that worldwide. And we find some interesting patterns of the frequency of cyclonic versus anticyclonic updrafts. So you can see that over the mid-latitude oceans or subtropical oceans, cyclonic updrafts are strongly dominant, but in the deep tropics, you see about in equal quantities of both of them. Meanwhile, over land, you see both cyclonic and anticyclonic updrafts as well. I should point out when you go to the more extreme updraft helicities, like for supercell thunderstorms, you see a predominance of cyclonic storms. But for the weaker updrafts, you do see that more equal numbers of cyclonic and anticyclonic updrafts. Now, the other question is, how does warming affect explicit convections? We did a simulation with plus 4K SSTs. My colleague Kai Chang did this work. This is somewhat idealized warming, but we found that continental convection generally shifts to a higher latitudes under this SST warming. We do generally see that there's more intense convection of updrafts greater than 10 meters a second. But in the mid-latitudes, they do shift more towards the high latitudes. And this has some interesting implications for water resources, especially in the Great Plains, where much of the precipitation during the growing season comes from mesoscale convective systems. Speaking of which, my colleague, there's been a lot of work on mesoscale convective systems in SHiELD and the other Diamond class GSRMs. Of course, as you might expect, these GSRMs do have a more realistic climatology of MCSs than a traditional lower resolution GCM, like the 25 kilometer C384 AM4 developed here at GFDL. And indeed, SHiELD does a fairly good job at representing this climatology. Most GSRMs also represent good, correct diurnal cycle of MCS precipitation. This is this study done by a couple of colleagues, especially out of the Pacific Northwest National Laboratory. Most GSRMs, there's one or two that for some reason don't capture this very well, but SHiELD actually remarkably matches the amplitude and phase of the diurnal cycle, especially over land, which I should point out might be fortuitous, but it is a good sign that the GSRMs and especially SHiELD really do an excellent job at capturing not just the convection itself, the convective cells, but how those convective cells interact with the larger scales to aggregate and to correctly represent how they appear as a larger scale aggregated system, which is going to be important. It's not just the small scale radar red dots that's important about simulating convection. It's how that convection interacts at the largest scale. And that's going to become important whenever you're doing simulation beyond just a few hours. We took a look at precipitation a bit as well. One interesting thing is this Western snowpack project. We could take a look. One of the things I like to say about orographic precipitation is resolution is paramount. And that higher resolution, as long as you have a good model, it's an easy win to get you better orographic precipitation. And indeed, in our 3 kilometer SHiELD, we greatly improve upon the 50 kilometer high res AM4, especially in getting the precipitation in the right spot over the mountains. Now, we did some interesting experiments with a warmed climate integrations. This is a paper by my former postdoc, Sung-Lin Shea, now working at First Street. This is just accepted to Climate Dynamics, so it should be coming out in the street soon. Virtual streets, excuse me. We found this interesting result that under warming, snowpack certainly decreases in most places, but the high mountains of California are high enough that they stay below freezing during most of the winter, and that California might be able to hold onto its snowpack during under even a fairly strong uniform SST warming, which is, again, interesting implications for water resources out there. And I had a lot of other results. I didn't think I had quite time to cover them all. One interesting thing is that there was a lot of hype, you could call it, that global kilometer scale simulation was going to solve a lot of problems for weather and climate modeling. is issued as kind of a panacea. And is that true? Well, global storm resolving models, you can do a lot of cool stuff with them that you couldn't do with traditional GCMs, traditional regional models. But it's not a panacea, and there's still a lot that you can't resolve. Things especially relating to climate sensitivity, like shallow convection, stratocumulus, you don't resolve those or even crudely represent those in kilometer scale models. You need to go to much higher resolution, and anvil clouds too. So climate sensitivity isn't going to be solved by kilometer scale modeling. Another thing that's a bit more prosaic is that this observed land-sea contrast, it's a bit controversial whether this exists or not, but the GSRMs don't capture it. I mean, one or two of them, I think ICON and maybe UKMO's model is able to do that. But most of the GSRMs, including ones that ordinarily do very well, like SHiELD, they don't capture this observed land-sea contrast. And we find out this is tied to how shallow convection is represented in the model, which you still need to parameterize because you're not even close to resolving shallow convective clouds at 3-kilometer resolution. Just the processes are still going to have to be parameterized. So look for this paper soon by my colleague, Tristan Abbott. Finally, I want to talk about some new technologies that we're doing with as part of the Global-Nest Initiative. One of these, the integrated physics, I unfortunately don't have time to talk with, but another one is our project to work with GPUs. And we've heard for years that the era of CPUs, massive CPU systems that are connected via massive passing interface libraries, that era is ending, and it's going to be GPUs for all our computing purposes. And we've been hearing this now for over 10 years. It's becoming a bit more closer to reality in recent years. Systems are coming online nicely. A lot of people are still going to be running these models using CPUs. So you're in the conundrum of which, okay, you have a model that you need to run well on CPUs. You want to run it on GPUs. There's a bunch of different kinds of GPUs. You need to optimize for each new vendor's GPUs. What are you going to do? And are you going to rewrite the model every time that you come out with new GPUs? Well, some people do that. They do refactor their codes for GPUs. The results are mixed. It's unsustainable, unfortunately. And indeed, there's been excellent FV3 ports of the FV3 Dynamical Core to GPUs using OpenACC. They get good results. They aren't sustainable. The goal of something like what we call GT4Py, Grid Tools for Python, this is a domain-specific language developed in Switzerland that they've written their Cosmo model in, is for performance portability. You write everything in a generic framework using a dialect of Python, and then it can be ported easily or it can be translated into machine compilable code specific for a CPU or whichever kind of GPU you want. And this gives you both performance appropriate for every single processor, as well as access to the whole Python ecosystem for debugging, instrumentation, graphics, machine learning, and what have you. This effort right here of rewriting FV3 and GT4Py, we call that PyFV3. It was started by the Allen Institute for Artificial Intelligence. Now it's in NOAA, NASA, broader community collaborative development. I should point out GT4Py does not exist in a vacuum. It's being evaluated also by the European Center and the Max Planck Institute in Germany. So there's a whole community growing up over GT4Py. The original port of just FV3 by itself, called PyFV3, showed significant speedups on GPUs versus the existing Fortran FV3 on CPUs. On an older P100 GPU system on PIS-Diane, it scaled to fill the whole system, as well as you're getting excellent speedups, a factor of 3.6x over the Fortran code on CPUs. If you use the newer A100, newer and quite a bit more power hungry as well, we saw an even bigger speedup of 8.6x. This is just dynamical core, but it really does do a lot to show what you could do with GPU acceleration, stuff that is already done. This is functionality that already exists. And indeed, it is already being used by our partners at NASA Goddard. They have implemented PyFV3 on GEOS, NASA GEOS, the rest of the code remaining on CPUs. Combining CPUs and GPUs, it's a challenge because you need to transfer data between the two different kinds of cores. On most, except for the very most recent NVIDIA systems, that's real slow. It's a real bottleneck. But they've done a lot of work, and even with running most of the code on CPUs except for PyFV3, they can see they get a pretty good speed up. They get a 2x and plus speed up for the whole model, not just the dynamical core, the whole model on their GPU systems as well. So that's one way of doing it. Now you can go even farther. We can think about rewriting the entire entirety of SHiELD in Python using GT4Py, physics and dynamics, have it all running on GPUs, all in Python. And this is a project we call PACE, being, again, this is a collaborative community effort. We have PyFV3, it's already imported. Most of the parameterizations in SHiELD have been imported into PyShield. We're currently working with the radiation scheme right now. We might bring that in as a Python wrapped GPU accelerated component. We're wrapping up the FMS framework as well. So we're real excited about that, what we can do within the next year. I do encourage you, if you're interested, PACE is downloadable, and there's a nice container for it. You can be a part of this new development at the address shown here. One other thing that I know everybody's been talking about lately is artificial intelligence and machine learning. And sometimes they ask, well, where is NOAA here? And well, I'm glad to say NOAA has been working with the Allen Institute for Artificial Intelligence at Excellent Institute in Seattle, founded by Microsoft co-founder Paul Allen. And we work with a team that's been led by Chris Bretherton, one of my fellow University of Washington folks. And they've been working on a variety of different machine learning techniques over the last 6 years now, I believe, in collaborating. And their initial work was on what was called corrective machine learning, in which they took a low resolution model and then nudged it towards SHiELD, coarsened SHiELD model output. And they trained those nudging tendencies, essentially the error correction, and use it to correct a free running low resolution model. This 200-kilometer model is 10,000 times less expensive than SHiELD. And they found that even with this corrective machine learning, you're running the full dynamical model with machine learning corrections put into it, and you see some major improvements in land precipitation, diurnal cycle, and surface temperature by doing this corrections. They've been able to find some pretty neat results with that. So this is one example we can do with this. Has been transitioned into NOAA HPC. We've been doing some nice experiments of this on a snowpack as well. One thing I should point out is that 10,000 times less expensive number is that you get what you pay for. If you had a great 200-kilometer model, it still can't resolve what a 3-kilometer model like SHiELD can represent, which is interesting in terms of some of the claims being made for some of these otherwise excellent AI models that people have said that are much faster than SHiELD. Well, you get what you pay for. AI2 has pivoted towards now doing full model emulation with their AI2 climate emulator called ACE. This is a fully ML data-driven model that's been trained on both ERA 5 and on SHiELD, a relatively low-resolution 100-kilometer SHiELD climate simulation. And this has been able to make some major accomplishments, some major firsts. In particular, it remains stable and is realistic, and mass and air, dry mass, water conservative out to 100-plus year rollouts. So it can follow an AMIP simulation pretty well as capturing some of the variability from year to year in SHiELD. So it's able to capture both the mean climate, the climate trends, and the variability quite well. And they've been doing some experiments with a slab ocean as well to be able to capture some of the climate sensitivity. And they're still shaking some of the bugs out, but otherwise they did some really cool stuff with this emulator, showing that you can use this to do climate simulations with. And there's a lot of possibilities for an emulator. I think it's a great complement to the full strength, industrial strength physical model. I think they make a great complement. In particular, you can run huge ensembles with something like ACE, which really opens the door towards a lot of awesome possibilities. They're doing a lot of really neat stuff to advance this, and I'm looking forward to what they can do soon. And then we can go even farther to a sub-kilometer scale. I mentioned this a little bit earlier, but we can take advantage of the capabilities of FV3 to do multi-nesting in a global framework, or to run a doubly periodic domain to do like radiative convective equilibrium, LES, and so on, to get down to 100 kilometers grid spacing, or even tens of kilometers of grid spacing, to start to do studies on things like cloud properties, force shallow convection, radiative convective equilibrium. There's this recent publication by a couple of my colleagues on the finger-like structures in hurricane eye walls. We've nested down to 125 meters. And we're able to capture the dynamics of these features very well close to what was observed in real hurricanes. So that shows that there's really a lot you could do beyond even the 1 kilometer scale. And are working also in our teleshield model, multiple nesting down to 1.4 kilometers for realistic hyperlocal prediction. In conclusion, our FV3 global nesting offers a world of possibilities. I've shown a number of different possibilities with that. The other thing is that storm scale, kilometer scale climate modeling has truly arrived. I remember one person saying that I might not arrive until the end of my own career and hopefully another 20 years. It's here now. So this is really cool possibilities. year-over-year improvements add up. Each new version may only be a little bit better than the past, but you do it over and over again, you'll get better and better and better. Just keep iterating. And finally, I'm stealing a quote from Richard Feynman here, that there's a lot of room at the bottom. And you can go, when you go to increasingly high resolution, you start to resolve some of these interesting features that have both scientific and practical interest. And finally, I want to acknowledge the excellent team that makes all of this possible, all the people that I work with. Yeah, I'm really glad to work with our partners, both here at GFDL and within NOAA and within the broader community as well. It's an amazing opportunity. I'm really humbled by all the amazing things that everybody's been able to do with the new FV3-based modeling in NOAA and elsewhere at NASA and at the other community partners. Thank you. That is the end of my talk, and I'd love to have your comments and questions. And if you would like, come and visit the websites there for more information. Thank you so much.
Thank you, Lucas. So now it is time for our Q&A. So there's a lot of you here. So if you could just raise your hands and I'll cue you when you have a question, and I will you'll all have the ability to unmute yourself. Or if you don't have a microphone, you can just type the question in the chat, or you can just type in the chat that you know, some people don't know how to raise their hands. So definitely feel free to just let me know to cue you. Don't all ask at once.
Oh, thank you, Ralph. Thank you for your comment.
Mm-hmm.
One thing I didn't have time to show in my regular talk, but I did want to give a couple of what I call challenges to the community. So if nobody has any questions, I can, oh, absolutely. Yes, I'll be able to send a copy of the slides later. Absolutely. Thank you. Thank you, Tanya.
Yeah, Lucas, if you want to send me the slides, I can send you my email address. I'll put it on your seminar site, so then everybody can just see it in one place.
That's fantastic. Thank you so much.
Mm-hmm. And I should also say that the recording of this seminar will go up by the end of the week on our YouTube channel,
Awesome.
Which is just ESSEC UMD. I'm a little bit behind on recordings right now because I just came back from leave, so please give me a little bit of time. Oh, the questions are in the chat now, so I'll go ahead and read them. Fang Lin Yang says, Lucas, great presentation. Can the parent and next use different die core options? For instance, trace numbers?
Yeah, tracer numbers. Yes. So thank you, Fang Lin. And also, I want to really acknowledge the great work that you and your GFS team have done over the years. I mean, you've really made the GFS into a truly world-class model, especially for tropical cyclone and high resolute and smaller scale phenomena, more intense phenomena. So I really appreciate all the work your team has done over the years. And indeed, you're right. The parent and nest can use different die core options. Trace is a little bit tricky, given that you need to figure out how to use boundary conditions for the different grids. So it's something that it inherently doesn't support right now. That is something that could be put in if there is indeed interest. So thank you, Fanglin. But other options, yes, there is. Yeah, you can choose them as you'd like. You can choose different diffusion and convection options. You can choose a variety of different levels. The other thing you can do actually is you can use different vertical levels on both the nest and the global domain. So in particular, as long as your nested grid top is below your coarse grid top, you can use an arbitrary set of levels on both the nest and the parent. So thank you, Fanglin. Excellent question. Next question is from Jim Purser. Yeah, so do you want me to read them off or yeah, I'm okay to do that.
So Jim says, can your nest straddle edges and corners of the cube?
Okay, not quite yet. That's supported in FMS, especially over the edges. The corners is a bit more challenging due to the different topology of the cube sphere at the corners. But it is something that we are interested in. There's two ways of doing that. One is to make the edge across the edges. You can make the nest follow the edges themselves. That will require some die core changes, but it is possible. The other possibility is to implement a floating nested grid that isn't necessarily constrained to follow the coarse grid. There's a little bit of loss of accuracy in that, but that could be something that could be implemented if there is indeed interest. Again, it's something that's just chalked up to, yeah, can we find the people to do these things, knowing that we're all quite overstretched. I know there's a lot of us doing excellent work. So, but thank you. That's an excellent question, Jim.
So Toshi has his hand up. Toshi, do you want to go ahead and ask your question verbally?
Yeah, the Lucas, it's excellent seminar. I learned a lot, and then hopefully government can keep funding this excellence model for the future predictions. So besides that, in terms of GPU and a CPU, yeah. So we had a discussion in the past 10 years, and then GPU starts having more feasibility for the geophysical fluid dynamics modelings, but yet, world fastest computer for the fluid dynamics is Japan, the Fugaku supercomputer, still like 6 times faster than the the GPU machines in terms of vector computer for the fluid dynamics. So I know it's a really transitional times, and then my question is what, like you said you're gonna have a hackathon supercomputer. Either NOAA is having a big planning to move toward the GPU machines or sort of a hybrid machines, or what is your visions?
Okay. So when it comes to GPUs, yeah, I'll come back to the hackathon in a bit. But when it comes to GPUs, NOAA is slowly getting some GPUs, and in fact, that's actually been the main bottleneck in our work. Is that we simply haven't had GPUs because all of our codes are CPUs, but we can't develop the GPU models because we don't have any GPUs because we're all running all on CPUs. So. But with that said, NOAA is slowly getting machines that does have some GPUs on it. I know the NOAA system has some GPUs that are usable. And we are getting some GPU capability here at Princeton as well, which is an exciting possibility. But it is true that a good CPU-based system with a good optimized model still gives you excellent throughput. And it's Fugaku, right, is an excellent example of that.
Yeah.
Plus, also, it's a little bit unfortunate, but some of the GPU advantages have been a bit overstated. I mean, at one point, people were talking about like 100x speedups from GPUs. And when it comes to running a full model, you get a 2x speed up, and well, okay, that's still pretty good. I know that in some agencies, especially DOE, all they have is GPUs. So that's what's really moving them is that, hey, you need to run on GPUs because otherwise you won't get any computing time.
Right.
But I do think there's a lot of exciting things we could do with GPU acceleration still. And I think it's going to be important to get on that because a lot of development is aimed at GPUs.
Okay.
Yeah. Now, regarding the hackathon, I should point out that the hackathon is part of a larger global project between centers at different sites. So there's going to be a node in Berkeley. There's a node in Boulder as well. And that's a global effort to do basically like analysis on global storm resolving models. So that's coming in May. All the different centers are going to be doing that at the same time. So thank you for bringing that up.
Okay. All right. Thanks.
Yeah. Well, thank you, Toshi. Okay.
Our next question is from Anna Rita Mariotti, who, fun fact, gave an Essex seminar almost exactly a year ago. So Anna Rita says, "Hi, Lucas. Great talk. Regarding the nesting approach, I am curious about what happens outside of the nests. Can you comment on the sensitivity to the nests, i.e. what you are not representing with the higher resolution, and how does this affect what's in the nests?"
That's an excellent question. And it is true that, the nest, one of the things about nesting is that you have to think about how does stuff get off of the nest. And of course, there's always problems when you have a abrupt discontinuity in your model, like at the edges of a nest, you might get some discontinuity artifacts. Now, with that said, there is a bit of a challenge in representing how that changed from higher resolution to lower resolution. And it may not necessarily be the case that what goes on in the higher resolution necessarily is going to feed back to the global scale correctly. And indeed, that is something that we had to struggle with in developing the MJO nested model. And then there's other issues like, you have explicit convection in one area that's going to give you very different qualities than the parameterized convection outside of it if you're down to explicit convection scales on the nest. So there are a lot of different issues with that. And that comes down, I think, more to development more than anything. And when you're doing this, you got to make sure that not just you get good nested grid characteristics, but you have to make sure that it's playing well with its parent. So I think that's my kind of naive answer to your question, Anna Rita, but that's my off the cuff conception of all that. So thank you.
So the last question in my queue is from Yamzu. So, oh, not the last question anymore. So they ask, the forecast scale of MJO with the nested maritime continent 3 kilometers is very impressive, up to 39 days. What is the additional cost running a 3-kilometer nest over maritime continent in a 13-kilometer global model compared to a 13-kilometer global model alone?
Usually the cost is about a factor of 2 to 3, depending on how big your nest is. We do find that the nesting itself adds relatively little overhead. So as long as you load balance the nested in the global grid correctly, you can usually get pretty good throughput when you're running a global nested configuration. Again, it mostly does come down to like, what are you doing on that nested grid? Like how big it is, how many vertical levels, if you're using more sophisticated physics and so on. But thank you, Jan.
So the next question, great talk. Thanks, Lucas. Has the sub-kilometer FV3 implementation been tested for real world or non-idealized cases?
We have not tested that for realistic simulations below 1.4 kilometers. There may have been some people out in the community. I know that at one point NASA Goddard was doing some experiments trying to run LES scale down to 500 meters, but we've been focusing mostly on process modeling simply because it's hard to get good data to fill in at 500 meters. And I know this is true for a lot of people. The only counterexample to that is the UKMO that does run an operational 100-meter realistic simulation. But yeah, the big limitation is that, simply that we haven't got to that, and sometimes it's hard to find the data to go down to that high resolution and still get a useful realistic simulation. But that's an excellent question. Thank you, Sudhir.
Thank you. So that's all the questions that I have currently. Does anyone want to ask any questions while we still have Lucas here? Okay, well, we are just about at the hour anyway. So thank you so much, everyone, for attending, and thank you so much to Lucas for giving us this great talk. I think that actually beat our attendance record for the semester. So that's really exciting. Thank you everyone for being so engaged with our series. So our series will continue next week. John, please correct me. Is there one next week? I'm not seeing anything. Oh no, because it's spring break. I'm so silly. It's UMD spring break. We are not continuing next week. Please look out for John's email about the next speaker. So thank you, everybody.
Yeah, thank you, everybody. You've been a fantastic audience. And thank you, Kazi and John, for inviting me here. And thank you, Ralph, for your introduction. Thank you all so much.
Yes, of course. Have a great afternoon, everybody.
Thanks, Lucas. Bye-bye.
Thank you. Bye-bye.